Hi, everyone. Thank you so much for joining us today in our webinar about marine life preservation solution with Voyis and VideoRay. I'm Patricia, the marketing manager at Voyis, and today presenting the webinar, we have Brendan, our head of ocean sciences at Voyis, and we have Brad, the global account executive at VideoRay. Just to quickly give you an introduction, the webinar is going to take approximately 30 minutes, and then we're going to have 10 minutes for questions at the end. So we're going to go through a quick introduction, then a little bit about the image project, and then Brendan is going to go over the Voyis solutions, and then Brad will go over the VideoRay solutions. So yeah, let's get it started.
So firstly, thank you, Patricia, for the introduction. And I also want to thank VideoRay for partnering with us to further discuss this amazing technology. Welcome, everyone, to our joint webinar about the image project. Personally, this is one of my favorite projects that I've been a part of. And to date, it's our biggest project focused on MPA monitoring and coral modeling. So let's get into some of the details right away. So the location chosen for this project's implementation is Howe Sound in British Columbia, Canada. This region is home to a substantial population of live glass sponge reefs and is a unique habitat found exclusively along the Pacific coast of Canada and the United States. The ecological significance of these reefs cannot be overstated. They play a critical role in filtering and processing carbon and nitrogen within the environment. And additionally, they provide shelter and support for a diverse community of marine species, including some economically important ones like rockfish, spot prawns, lingcod, and crab. So despite their ecological importance, glass sponge reefs face threats from human activities, especially bottom contact fishing and sedimentation. So to try and safeguard these fragile environments, Oceans and Fisheries Canada has established marine refuge by enacting fish enclosures. Now, the issue is due to that slow growth rate of glass sponges and their limited recovery capacity, this demands continuous monitoring and adaptive management strategies. So in response to these challenges, Voyis contributes significantly to the project with its cutting-edge optical systems, the Insight Micro and Discovery camera. These sensors enable researchers to acquire high-resolution, color-corrected 3D data of the glass sponge reefs, which can be used for accurate photometric reconstruction of the ecosystems in order to produce a complete digital twin model. So these volumetric models can be compared to subsequent surveys to detect changes in reefs' health over time. The ability to deploy these solutions remotely on autonomous vehicles improves the efficiency and effectiveness of the monitoring solution. So the project has two main deliverables. Firstly, the 3D models, which will be used as a baseline to detect changes in the health of the reef for comparative analysis to data collected in future surveys. And the second being to help with governance of the MPA. So this means to identify illegal fishing activity that could be taking place in the protected areas. And we were actually able to achieve both of these goals, as can be seen obviously in the models being shown today, but also in some of the image and laser data, one of which we actually clearly identified a net embedded in one of the reefs. So next we'll go on to one of these really cool models that we collected. This is a forward-facing camera model of a reef on a cliff. So along with the deliverables, there were also four major goals we wanted to accomplish with the project. The first goal was to develop a viable monitoring system using our equipment, a solution that could be deployed from a dynamic platform like an AUV or an ROV to allow efficient and remote monitoring of these MPAs. The second goal was the project was to collaborate with the indigenous communities through training and mission planning. So the traditional ecological and environmental knowledge provided by these communities is invaluable. The project looked to help empower indigenous communities with a technical capacity to actively participate in marine and environmental monitoring and ocean conservation planning. Next was the physical survey of the habitat and the analysis of the data. So it was important to work with different resources to effectively build out mission plans that would allow us to obtain the necessary data for analysis of the habitats of interest. And so the final goal, once again, focused on governance and education. This included disseminating data that was collected to help ensure further education and inform the development of novel methodologies, as well as site establishment. Additionally, we looked to perform some assessment of an unsupervised training method, which automatically clusters the image data into a structured database. From there, representative images can be selected for each feature of interest. So something like live reef versus dead reef, or any other feature of interest within these images, and then geospatially mapped to understand the distribution. With this new technology, researchers can enhance their conservation plan and decision-making. So the video that is currently being played is an example of stills image data tied to transects performed by the vehicle. The singular images that are represented represent an average image found within that specific cluster at the provided location. All of our images, once again, have georeference on it, and that's partially the reason why we are able to do this. Perfect. So now let's talk about the project, and we'll focus a little bit more on the actual technology that was used to obtain the amazing results. So here at Voyis, we've been working for some time in collaboration with VideoRay to enable the deployment of our sensors from their vehicle. So for this project, we equipped the VideoRay Defender with the Voyis Discovery camera for enhanced piloting and forward-facing data collection, and a perception skid for downward imaging and laser scanning. And finally, a Sprint Nav Mini for improved navigation. The Defender is an optimal vehicle for this application, as it's got maneuverability, which helps ensure that we are able to obtain the proper advantages of the target. And this is important to collect data from all angles. So now a little bit more about Voyis as a company. I want to provide you with a little bit more information and take a deep dive into the specific systems that were used on this project, their capabilities, and their functionality. So at Voyis, we look to provide versatile optical solutions that expand your underwater capability and enhance the understanding of remote challenging environments. So we're able to accomplish this by using subsea laser scanners and digital stills cameras with data enhancements and corrections on board the sensors to enable real-time analysis of data on the fly. So as you can see, we provide standalone sensors, but also a few different offerings that are a combination of our core products, so the laser scanning and stills imaging equipment. So jumping into more details on the products, first up is our Insight underwater laser scanning systems. So I'm not going to go into much detail about the different models. If anybody's interested, by all means ask afterwards, reach out. But I want to expand a little bit more on the Insight Micro, as this is the system built into the perception skid, and this was the equipment used for the downward collection portion of the survey. So the Insight Micro is a dynamic laser scanner that enables small vehicle platforms to perform high accuracy inspections by combining both laser and stills imaging equipment into a singular package. So as you can see there, we've got the built-in stills, laser emitter, and LEDs all in one single package. So now kind of a little bit about how does the system actually work, its functionality. So the system provides gapless laser data such that the two technologies cause no interference to one another and work harmoniously to collect dual data sets of the same target. This is achieved by capturing stills images in the short time in between laser pulses. So this helps ensure that there'll be no visible laser lines in the stills data, and vice versa, that the flash from the LED will not wipe out the laser line. The laser itself projects a 50-degree swath, which is swept across the target. This line is comprised of a series of individual points, which are triangulated based on a fixed distance between the laser emitter and the laser receiver. And then all of the data from the point clouds can be viewed in real time by the topside operator as the data is being collected. Now, obviously, the caveat to that is it has to be a tethered vehicle. Otherwise, all the data will be saved on board the sensor itself. So next, we will jump into the discovery systems. So the Discovery Vision systems were designed to avoid compromise between using a piloting camera, which prioritizes low latency over high quality data, and inspection cameras, which tend to prioritize high quality data over low latency. So this is made possible by utilizing the latest in the next generation computing hardware with top quality optical systems. So as mentioned, these systems deliver real-time data in a low latency piloting feed. Everything is onboard image corrected, high resolution videos, stills images optimized for photogrammetry. And in the case of the stereo camera, we provide also real-time depth maps. So all the data sets are processed on the edge, including the image and video enhancements, such as the light leveling, the undistortion, the color correction, and light balancing that we apply to all of our images across all of our image systems. Finally, the data sets are all optimized to enable operators to create 3D models of the targets or critical infrastructure in order to gather complete understanding and digital representation of the overall environment. So the Discovery Vision systems include an inertial movement unit to track position. We also include factory calibration. The images store position information within the metadata. And finally, the cameras leverage a global shutter, which is in comparison to a traditional roll-in shutter, will elongate the targets while they're moving. So this is an example of some comparative images collected from a standard ROV camera versus our Discovery camera, and this is in a low light situation. We can see the Discovery camera provides a clear representation of the target. So this is largely because it leverages a high dynamic range with 12-bit depth, uses a global shutter rather than a roll-in shutter, and also captures images at extremely low exposure times. So coupling all of this with the real-time enhancements of light leveling, color correction, and distortion, it shows the quality of the data, which will be used to help improve efficiencies in ROV operations. Here is another example of a 3D model that was generated using images collected from the Discovery camera. We just deployed the camera from a VideoRay Defender vehicle. This model was made using off-the-shelf photogrammetry software, and then obviously the images generated from the Discovery camera. So I think this model kind of perfectly exemplifies the ease in which the final product can be obtained when utilizing really high quality data for model generation. Now, in saying all of that, I think it's important to take a closer look at the process which allows us to obtain these high quality images. So one of the key features to our imaging systems are the real-time correction algorithms that get applied to the data. All the images collected from our imaging solutions are run through a series of algorithms to help enhance the quality of the image to correct for the underwater environment. So firstly, the images are subjected to an undistortion and debarring process. From there, the data undergoes light leveling to establish even illumination across the entire image. So there's no dark edges or corners, which is very important when looking to build out photomosaics or photogrammetry models. And finally, the images are color corrected. However, the actual hardware being used to collect the data plays just as much of a role in the quality of the data as the enhancements algorithms. So one of the key features that makes these enhancements possible is leveraging dynamic range to its fullest extent. So here, this example shows how bit depth within the camera can be critical in bringing full details to light in the data sets. So with an 8-bit camera, there is 255 levels of color per individual pixel to play with and correct in order to optimize the image. Now, if the image is too dark or too light, the pixel color may exceed the boundaries of the color levels, and this will result in oversaturation, which you can see in the corner of the middle images there. This leaves the images muddy, and the result is that important details from the image tend to go missing or get overlooked. Now, with a 12-bit camera, the enhancement algorithms have access to 4,096 levels of color per pixel. So this results in a substantially more detail to be maintained and provides even correction in both light and dark environments roughly equally. This, accompanied by fixed focus lens, is critical in maintaining a consistent data set across subsequent images, which is critical for building out photogrammetric models. Finally, next is our true color correction. So naturally, blue and green wavelengths penetrate the water farther and more predominantly than reds. This results in images with a blue or green hue, as can be seen in a couple of the images there. So in order to bring out all the details of the target, we need to remove the visible hue from the images in order to represent the target as if it was in air. Additionally, by illustrating the true color, we also bring out more definitive features of the target. So an example of this can be seen in the comparison of the two checkerboard images on the top and bottom right of the screen. So we also use machine learning approaches to our color correction, where the color model will continually be improved as more images are taken within a survey location or environment. So lastly, we will move on to the perception skid, which was equipped to the bottom of the VideoRay Defender for the image project. So the perception skid is a pre-integrated skid incorporating all the sensors required for dynamic laser scanning and imaging, while dramatically simplifying the integration process. So the skid has been designed such that it will not impact the operation of the vehicle and is neutrally buoyant. The solution also offers autonomous command and control options using softwares like IVA Mobula. So the perception skid has all the sensors required to conduct dynamic laser scanning, while also capturing 4K resolution color stills images. Like I said, the skid is neutrally buoyant and will be designed to significantly, my apologies, specifically for mechanical and electrical integration to the inspection and observer class ROVs. Additionally, we embed a SprintNav Mini for increased navigational accuracies, which in turn also helps improve the quality of the 3D point cloud and photogrammetric models. Now, finally, I want to touch on a few of the various applications that ocean science focuses on and that the systems are commonly used for within that space. So the ocean science sector is actually quite interesting as aspects of it actually span across all four major markets that we cover at Voyis. However, there are traditionally three applications that we focused on in the past. So firstly, area mapping and marine archaeology, building up models and maps of wide areas or specific archaeological sites. And I'll show a couple examples of that later on. Next would be benthic habitat and coral monitoring. This application tends to be centered around the monitoring and analysis of MPAs, their health and changes over time. So very much in line with the image project that we just completed. And finally, flume tank and lab-based inspections, where we have a non-intrusive laser that's fully submerged and capable of identifying sediment transport, scouring, and ice-based research. So very much flume and basin-focused research. So now just a couple more examples of projects that share similarities to the image project and highlight some of the capabilities of the system. So to wrap up the Voyis part of the presentation, and before I hand it off to VideoRay, I wanted to highlight another recent project that we completed. This was with Memorial University and Schmidt Ocean Institute. We were really lucky to be a part of this project, and we provided the InSight Micro to capture data in the Galapagos National Park. Once again, the focus was on the imaging and modeling of corals to help determine the health. So we put a pretty small role in the project, as obviously there was a lot more to it than just the imaging and modeling of corals. But we're actually able to help identify 2 pristine reefs surrounding the Galapagos. Now, unfortunately, I can't share a lot of the data as of yet because it's still a fairly new project and a lot of it hasn't been released. But I can show a couple of the highlights, which really show the amazing ecosystem and how it's been preserved by conservation efforts. So here you can see an example of some of the laser data collected. And this here is pictures that were collected during a survey, one being on your left-hand side, a downward-facing laser scanning of some seabed, and obviously we were able to capture a little bit of a fish, and I have some really cool corroborating images to go along with it. And then on the right-hand side is a coral bed with various different types of coral species. Working with Schmidt was really amazing because we were able to devise a mechanism that would actually allow us to adjust the angle of the scanner on the ROV. So we could do downward facing seabed scanning, as well as adjust the angle to 45 and forward 45 degrees, and a complete forward facing system to scan and model faces and vertical faces of various cliffs and walls under the ocean. Here you can see a comparative image of a comparative example of some laser and stills data. I think this picture is a good indicator of why it's beneficial to collect the two different types of data sets. One, obviously, you can see the benefits of laser can provide volumetric analysis capabilities, and the other being a stills image, which highlights the color. And in many cases, knowing the color of the species is helps classification, and can also be, in the case of coral, a good indicator of the health of the corals. Finally, just a few more examples of the laser data collected in various subsea environments, and just to highlight the type of detail that can be obtained using a very high resolution sensor. So here are a few more examples of the subsea corals in the Galapagos. This next one is just a little bit of seabed data acquired from our systems mounted to a Huygens AUV. So a fairly big AUV moving at a fairly high speed, and we're still able to obtain this resolution and this high quality data. And lastly, this is one of the many shipwrecks we've modeled. Once again, it's a great example of the level of detail that can be obtained using the laser system. We have a lot of subsequent imaging data that can be used to build up photogrammetric models of the same kind of targets. So thank you for listening to my portion of the project. I'll now pass it on to Brad so he can talk a little bit more about the ROV that was actually used for the project. So Brad?
Again, thanks for the introduction, Brendan. I'd like to introduce myself. My name is Brad Claus, Global Account Executive with VideoRay, with focus on markets of offshore wind, oil and gas, aquaculture, and science and research. It's something we're very excited with partnering with Voyis on. The capabilities of these camera systems are truly revolutionary, in particular to the inspection class vehicles. So that enhanced capability that you're able to offer in customers a true end product that I guess in the past we had to actually have world-class submersibles performing these tasks. Okay, and here I'll talk about our mission specialist products. We at the moment we offer two different submersible classes. One being our Pro 5 vehicle, and the second being our Defender vehicle. Mainly here we'll be talking about our Defender submersible, which is the same vehicle that was used for the scope performed by Voyis. Again, the vehicle is set up with a true flexible modular design. The ability to integrate and accessorize different components on the vehicle are very seamless and easy. The way that the vehicle is set up is on a Ethernet based backbone, to where you just truly have to mount the hardware to the vehicle, set up an IP address, and then you're up and running. For relentless reliability, I'd say it's best in class for this style of submersible. We're one of the only vehicles that actually offer a 2-year warranty for the product. In addition, I think to date, our longest dive time that we've performed on a site was right around 6 months. So again, another metric to attest to the reliability of the product. For intuitive operation, the software that we offer within the product, you can actually, even novice pilots, with what we offer for the 3-day and 5-day comprehensive training, these pilots, although unskilled, at the end of the 5-day training are very capable and competent in performing pretty complex tasks. For the ease of deployment and transportation, it's truly 2 Pelican cases and whatever amount of tether you may have for the scope that you're doing. When you compare that to other submersibles of the same class, some may require, truckage, craneage, welding, water bag testing, any kind of NDT testing as well. And that's all a big a cost burden to our end clients. So having that same capability or enhanced capability of our product, but still eliminating the cost for mobilization is a big plus for most of our for all of our clients in particular. So standard configuration of our Defender vehicle is a 300 meter rated. We can perform upgrades to the vehicle to make it capable at running at up to 1,000 meters. Now, in addition, we are currently working on options to actually take the submersible down to 3,000 meters. Again, max speed 4.1 knots. In addition, it has the ability to lateral overcome or lateral over 1 knot, and the ability to ascend or descend at over 1 meter per second. A couple different control options we offer. One is our standard OCC, which is a full PC power supply, 19-inch monitor, but we do have some other options to where you can go with a splash-proof controller. Again, IP65 rating, for if you're working in, I guess, less than marginal conditions, have any concerns with the elements, rain, etc., snow, to where you'd have that option to where it could actually work in those types of environments. Again, there's a ton of different payloads we could offer with the vehicle. Some to include, again, multi-beam sonars, scanning sonars, rotating manipulators. The one shown here that's actually on the vehicle is one of our more simpler manipulator designs. It does offer a parallel V-jaw, sampler jaw, trident jaw, and cutter, but we can offer, again, kind of task dependent of the customer's requirements. We could run with single or dual, 3-function, up to 7-function, rate controlled or spatially correspondent manipulators. Again, so it depends on what the tasks are, and that's what our SMEs are set up for, to understand the client's exact needs and create a build that'll meet their expectations. In addition, navigation package, so full semi-autonomous control, the ability to complete complex missions. Always use the analogy, the way that our navigations package is set up, to where if you want to inspect the area the size of a football field, you could simply plot out a region within the software of whatever predetermined region you want to inspect, hit go, and the vehicle will do the entire inspection on its own. Again, multi USBL systems, we offer a ton of different options on that as well. This is, I guess, truly the key to the vehicle is the modularity. The way the vehicle is set up, there's no 1 atmosphere housings. Everything on the vehicle itself can be swapped out pretty seamlessly due to the modularity of it. So flotation, the AHORs, power modules, batteries, DVLs, you could actually, the software could actually troubleshoot it down to the component of what it will be, and then it's simply if you have a failure, it's simply swapping out that component. We're geared up to where any component on the vehicle can be swapped out with a replacement, I'd say under 20 minutes or so. So again, the modularity of it is a big advancement. In particular, if you're working the vehicle in critical path operations where time is of essence, if you have the failure, at least you're back up and running very quickly. So there's a lot of different partners we're working with currently, some being dealers, some being manufacturers as well. This shows a couple of different the combination of dealers and manufacturers that we're working with, among others that are not included here. Again, we're very excited at working with Voyis. We're very thrilled about this technology being capable within this small footprint of a vehicle. And if anything else, if anyone has any questions, please ask.
Thank you everyone for joining. Later today, we will send everyone who signed up a recording of this webinar, just so you know. We do have a couple of minutes for questions, so feel free to send your questions via the chat, and we'll go through all the questions. We only have a couple of minutes, but feel free to send it over. So Brad and Brendan, we got a question here in the chat. So what kind of turbidity limitations of the skid? What are the turbidity limitations of the skid?
All right, sorry. Thanks, Patricia. Yeah, so it depends on the technology you're looking at. In terms of the forward-facing discovery camera, we've actually found that this performs very well in turbid conditions. One of the reasons this is because from some of the pictures you saw, we space out the lighting so that it's offset from the camera and not directly beside the camera. This helps ensure that we don't illuminate all the particulate directly in front of the field of view of the camera, kind of being like snow. It actually means that we illuminate the entire environment surrounding the camera, so you're not actually flaring up all that particulate directly in front of the camera. In terms of the downward-facing laser and imaging system, once again, the particulate for the imaging side of things doesn't hinder it too much for the same reason I just explained. In terms of the actual laser, it's not too bad. You do have to keep in mind that it's an optical-based system, so there will always be some impact caused by turbidity. But the laser itself is actually very good at penetrating through. So as long as the laser or the optical receiver can see the laser line on the surface of the object, you're still going to be able to acquire data. It might just slightly reduce the resolution of the data that you're collecting. Hopefully that helped, but if not, feel free to send me an email afterwards and we can go into more detail.
There's another question. What are the most common challenges you usually face in missions? So Brad and Brendan.
Yeah, and Brad, maybe actually to you, there's a question that looks like about buoyancy and pitch considerations / issues. So I'll let you take that one. Take that one afterwards. What are the most common challenges usually faced in missions? Once again, from our side of things, probably the biggest one is turbidity when it comes to the optical systems. But we have found ways to combat that, so it's not a huge factor. As a joint solution, I think we found that high currents can play a big role, kind of pushing around the vehicle, which is difficult to then collect really quality data. And it's just one of the challenges that you're going to face. But I think from our side, those are probably the two most common that we see when deploying the combined solution.
I don't know if Brad has anything to add. I think we have time for just one more.
Yeah, sorry. I think Brad's still muted. I'll answer the next one too. So in terms of robustness of the skid components, yeah, I know in terms of the vehicle and the Voyis sensors, they're very robust. They're actually designed and typically used in offshore environments, so being thrown around a lot, getting hit off off walls and off structures. The the one component that I would say is somewhat susceptible to damage would be the forward-facing discovery camera. It's got a pretty massive lens, as you can see, a dome lens, which is 130 by 130 field of view. That can be a little bit susceptible when you're getting towards a wall forward-facing or anything like that, and with currents, obviously, can kind of push into that. I wouldn't say that it would ever break, but it's in those instances can get scratches on the lenses and stuff. We actually had a project down in Chile where we noticed a scratch on the lens, but we were able to actually buff it out and keep going. It didn't cause any downtime or anything like that. And the bottom facing equipment, it's all protected. It's enclosed in the skid, so we're not really worried there. I don't know, Brad, if you're unmuted, if you want to talk more about the vehicle itself.
Yeah, Patricia, I'm sorry, the mute was locked. Could you rephrase that question again?
Yeah, so just a little bit about the robustness of the actual vehicle itself, in currents, in rocky conditions and stuff like that, how it fares in those situations.